Welcome to Power System Operation and Control course, in which the lecture module 1 consists of structure, evolution, and also we'll see the main requirement for the power system operation and control. Before going, as you know, this electricity is one of the important essentials for any development of any country and also for the mankind. The commercial use of electricity started in the late 1870s. However, the invention of the electricity took place very beginning. In the early phase of the electricity development or evolution, this was only used for the lighting purpose. There was generators as well as the loads. They were together and it was localized to certain local areas. The first electric power system, which started in 1982, and it was invented by Thomas Edison at the Pearl Street station in the New York, USA. This power system was the DC system, and it was consisting of the DC generators, the cables, fuses, and also the load. It was feeding the power to the 59 customers, and it was feeding in a radius of approximately 1.5 kilometer in that one. The operating voltage, it was 110 volt, and mostly it was giving load to the incandescent lamps, means simple bulbs. And at that time, the 4 generators of 25 HP, means HP were used, and it was the DC generator. In 1884, these motors were developed by the Frank Sprague, and they were added to this power system. And again, these were basically the DC motors. After addition of the motors, the use of electricity was very prominent, and the people thought that electricity is the better way to utilize the energy. But in 1886, the limitation of DC became apparent. The main problem of the DC is the high loss, because it was not possible to raise the voltage in the DC. It was only that people were using for the increasing the voltage by the several series DC generators in the cascade way. And adding this cascade, again, there is a lot of problem in the insulation that's between the different generators, and also it was not safe. At the same time, it was required that anyhow, if we can increase the transmission voltage or require the voltage so that the current requirement is less, at the same time we can reduce the voltage drop. At the same 1886, the transformers, as you know, the transformers are used for the AC power system, and the AC distribution system was developed by the William Stanley of the Westinghouse, and the Westinghouse basically here purchased the complete patent of this whole AC system. In 1889, the first AC transmission system was developed in USA. It was basically in between the Willamette Fall and the Portland, Oregon. At that time, it was not possible to use the DC system because the distance from this Willamette Fall and the Portland, it was more than 21 kilometers. So the DC was not possible that we can have the DC generators as well as the DC transmission. So the first AC single phase transmission system, which was the 4 kilovolt, and it was for this 21 kilometers. Then the DC becomes, it was not feasible, it was not even possible to power flow over the long distance with the DC. At the same time, there were the other development for the polyphase AC system, which was developed by the Nikola Tesla, and he had the patent of all these AC generators, motors, transformers, and the AC transmission line. At the same time, the Westinghouse purchased it. Then the controversy started whether we will go for the DC system or we have to go for the AC system. This DC, as invented by the Edison, he advocated for the DC system, but the Westinghouse, which had the patent for all the AC systems, then it was advocating for the AC system. At the same time, even the Edison wrote in the magazine that the AC is used for the killing of the people. because at that time in the very beginning, AC was used to giving the shock to the people. But no doubt, this AC won the match, won this whole scenario due to the several reasons that the voltage increase was possible. At the same time, it is simple to generate and to utilize the AC power compared to the DC power. So then this slowly and slowly this AC power become prominent and the DC was phased out. In 1893, the first three-phase line was invented and developed, and it was between this Niagara Falls, that was the 30 kilometers from California, and it was operated at the 2.3 kilovolt of the supply. This first three-phase transmission line was, again, it was the remarkable achievement in the three-phase system, and you can see right now we have the three-phase transmission system rather than the single-phase transmission system, especially in terms of the transmission. The early voltage, if you see that, witness that up to 1921, we had the voltage of the different voltages, like we had this 16 kilovolt, 44 kilovolt, even to 60 kilovolt. But later, from the 1922, the voltage keep on increasing. The reason behind this increase in the voltage that we can reduce the current, and therefore we can reduce the losses in the system. At the same time, we can reduce the voltage drop. So in 1923, the 220 kV voltage level was invented and it was came into the operation. Similarly, in 1935, it was 287 kilovolt, and in 1953, it was here 330 kilovolt. So you can see it is a continuous here. Voltage is keep on, people are trying to go for the higher voltages. Again, these were possible due to this, the insulation level, and also the right of way problem and the insulator, etc., the development at the same time. Then in 1990, we achieved this 1100 kilovolt AC transmission system. So it was, at that time it was realized that we should go for some standard, because it is a witness that the loads, they were very near to the load centers. The generation as well as load, they were put together. So then it was realized to have interconnection, and then for the interconnections, we should have the standard voltage level. So the standard voltage level again adopted the different standards for the different country, and normally the voltage level 115 kilovolt, 131 here 38 kilovolt, 161 kilovolt, and up to 230 kilovolt came into the category of high voltage transmission lines, and more than that, that 345, which is very common in the USA and Canada country. Here the 500 and 765 kilovolt transmission line, they were known as the extra high voltage transmission line. Again, if you will see the frequencies also, since a generator which was feeding load very near to that and it was not interconnected, so the frequency also it was varying. It was 25 hertz, you can see here 50 hertz, 60 hertz, and 125 hertz, along with the 133 kilohertz was also possible. But we know for the integration, we should have the same frequency throughout the system. So some country, like here in India and other Asian country and European country, they adapted for the 50 hertz operation, and the USA and the Canadian country, they just use the 60 hertz. So again, if you will see that in terms of generating voltages, since generators were earlier the DC, later they were invented the AC generators, and the voltage also they keep on increasing. They had the different voltage levels, and again it was possible. So far we have up to the 33 kilovolt transmission, the generation of generating voltage. And here in India even we have the 21 kilovolt generation. Then what we do, then we use some generating transformer to lift the voltage at the higher voltage, and then we transmit power to the over the transmission line. Finally, it goes to the customer through the distribution transmission lines. So it is well established that the generation as well as utilization is the suitable in terms of the AC part. Means AC generation as well as the AC distribution is the economical, cheaper and the efficient in terms of operation and its maintenance. But the transmission part, again there is some doubt that whether we can go for the only AC or whether we can go for the AC as well as the DC. If you will see, there are some advantages of DC. I will come to that point later. HVDC system, basically what we do, we normally connect the two systems with the different frequency we can do for. So the first mercury valves, basically they were invented here in 1950s. Then first HVDC transmission between the Sweden and the Gotland island of the Sweden itself, it was came into the operation in 1954. So this first HVDC transmission between the Sweden mainland and the Gotland island, it was not possible to interconnect with the AC transmission line, because this Gotland island, the operating frequency was 60 Hz. However, the main island, it was the 50 Hz. So, and also this distance was the 60 miles. So it is not possible to have a cable of more than 50 kilometers. So only the option at that time left that we should go for the HVDC. High voltage DC transmission system came into the existence, and this is the first which came into 1954. If we will compare the advantages and the problems in HVDC transmission system, let us first go what are the problems in HVAC transmission system. The main problem in HVAC system is, as we know, although I have written on the second point, it is your stability. We know this one equation here, that is a power, it's an approximate equation, that is V1 V2 upon X, that is the reactance between the S2 line. Here it is your sine delta, and delta is angle between the voltages here V1 and the V2. So we know this here, the maximum power which can flow in AC transmission system depends upon the voltages and this angle and the reactance of the line. This delta cannot be more than pi by 2 degree, that is 90 degree. So the stability concerns here is one of the big issue. Even though here the delta can be theoretically 90 degree, but we cannot operate our power system at 90 degree, because if there is some deviation, some fault in the system, our power system will lead to in the collapse state and unstable power system. So always we operate, this delta should not be, it should be always less than 30 degree or downward. So the stability is one of the big issue. So what we do, if our system is weak and the less stable, then we use some other devices to improve the stability of the system. Another is the reactive power loss. Reactive power loss is one of the, normally this first you have to go for the, you should understand the real power loss. Real power loss is nothing but, it is your I square R loss normally we call, or sometimes if loss is in the core, it is also real power loss. But the reactive power loss is nothing but the reactive power loss, that is I square X. X is the, you can say, reactance of the line, and this is the summation of other, which is the generated reactive power, and normally it is voltage square divided by Xe due to the charging of the transmission line. So the reactive power loss is one of the concern in the AC system. Another is the point third is the current carrying capacity of the transmission line or the cable. It is, you can know if your transmission cable is more than 50 kilometers and you are not taking a load at the receiving end, your sending end current will be even though more than its rating of the cable. What will happen if you are going to take even though a small amount of power at the receiving end, this current will exceed its rating and this cable will burn or rupture, and it is not possible to transmit the power. So that for the transmission line as well, it is not possible for going for more than 500 kilometers overhead transmission line, that is the bare conductors, and 50 kilometers for the cable. And this is due to the current carrying capacity, and always it is limited in the AC system. Another concern in the HVAC transmission system is the Ferranti effect. You know this Ferranti effect is nothing but when the receiving end voltage at the no load or likely load is more than your sending end voltage. So what we do, we normally go for some compensating devices, and normally we use the reactors if line is very long, we use the line reactors in the transmission system so that we can reduce the voltage at the receiving end. This normally happens if your system is collapsed and or you are energizing that line from your sending end, and receiving end, if it is a lightly loaded or there is no load, your receiving end voltage will be higher, and what will happen again, your protective devices, they will sense the voltage and they will again trip your transmission line. So it is not possible until unless you are controlling that voltage. So this is your Ferranti effect. Now let us see what are the advantages here in this HVDC transmission system. There are so many advantages of HVDC system, but also it has some disadvantages, and then we'll see some disadvantages as well. The various advantages of HVDC transmission system, that it requires less space. Less space in terms that we have normally the two-wire system. We may have the homopolar operation, we may have the bipolar operation, we may have the monopolar operation. So only we require the two conductors maximum in the DC system. And also here there is no compensating devices required, although we require the converter stations as well. So in overall, the DC stations they require less space. In this HVDC transmission system, we can also use the ground as a return path. Normally in the monopolar operation, this one is the positive current which is there, negative phase is there, then ground can be used at the return path where it is not possible in HVAC transmission system. Also, if you will see, the corona loss is minimum in this your DC transmission system, and there is no concept of the reactive power at all, so there is no reactive power loss in this HVDC transmission system. It is also it is cheap for your long distance transmission of power. So this HVDC transmission is cheap for the longer distance of the transmitting the power over the long distance. Now normally if you will see the cost of AC here, this is your, if it is a distance, and this is a cost we can write, then your here this is your AC system and this is your DC system. So the cost here, this is your, normally it is known as a break-even point here. So the cost, initial cost of the DC system is transmission system is more than your AC system, you can see here. But once it is a distance is more than this break-even point, then your DC becomes cheaper compared to the AC transmission system. So this distance earlier it was somewhere 700 to 800 kilometer, but now it has reduced to even to 605 to 600 kilometer. So if you want to transmit power more than 600 or 600 kilometers, the DC is the cheaper option for the transmission of power compared to the AC transmission system. Now, nowadays, it is not only the transmitting power, DC power from one end to another end, but we can also use this DC for the several other purpose. So normally the use of the DC is to transmit bulk amount of power and another is to control this power. Control of power is one of the big advantages of DC system. In AC we cannot control the power. If you know, the current always follows the minimum impedance path. So if AC system is interconnected, you cannot control the power over the transmission lines unless until if you are having the parallel lines, then one you can trip it, so you can change the impedance, then the power will be different in the different line. But here in this DC system, we can, that is a control the power. That is one of the greatest advantages of having the, like here I have written, this power control is possible in the DC system. Also this in the advantage, as we are looking at the advantages of HVDC transmission system, it has no skin effect. You know, this skin effect is nothing but here if you are having let's suppose this is your conductor. So current always follows the outer side from the center to flow in the AC system. So what it does, normally the resistance of this conductor is increases because the current is uniformly distributed over this conductor. So always this RDC, that is the resistance, if the DC current is flowing in the same radius of conductor, is less than your R if AC current is flowing in the same conductor. So this is due to the skin effect of this transmission line. And also, as we say, there's here the Ferranti effect. There will be no Ferranti effect in the HVDC system because there is no charging at all. The capacitance, no doubt they are formed, but it is not charging and it is not following any charging current over that one. So for the DC, this capacitance just behave as an open circuit in the steady state. Another the great advantage of HVDC transmission is that here asynchronous operation is possible. Asynchronous possible here, it is nothing but you can interconnect two frequency systems together with the help of the DC system. In the AC, always we must operate all our power system, all the electrical appliances, apparatus, elements at the same frequency level. But here in the DC, you can interconnect two different frequencies with the help of HVDC. So this is called asynchronous operation is possible. As we saw the example of the Gotland Island, which was interconnecting your Sweden mainland and the Gotland Island, both were operating with different frequencies. And then it was only possible to go for this HVDC system. So this is one of the great advantages that we can have the two different frequency system we can interconnect. Here also the short circuit power in the DC, here there is no short circuit. In the AC, if you keep on interconnecting, what will happen? The short circuit level at that point will keep on increasing, so that you have to go for the larger, the protective devices like circuit breaker rating you must increase. But here this is not a sort of that concept. Another the great advantage, which was the limitation of AC system, was that there is no stability problem. Here this formula doesn't apply. This here is V1 V2 upon X sin delta is no more applicable for the DC system. So the stability concept is no more there. So the DC system is much more stable compared to your AC system. If you will see the disadvantage, let us come to the various problems in HVDC transmission system. As we saw in the beginning, that the cost of the terminal equipment, even though the cost here, if you will see here, this cost for the DC is more here compared to the AC system. This is due to the terminal equipments of the DC system, because we require the converter circuit. Even though you are going for the shorter distance, you should have the two converters. One is known as rectifier, another can be as inverter. And again, we should go for other auxiliaries for these converter stations. For example, we should go for the cooling, because there will be losses in this thyristors or GTO valves, and we require a huge cooling and better cooling, otherwise this will get burst or puncture. So here this cost of the terminal equipments are very high. But nowadays, due to the development of very high power semiconductor devices, especially power electronics devices, then it is possible to reduce that cost as well. So nowadays the cost of the terminal equipments keep on reducing as we are going for higher and higher rating of the thyristors and other power electronic devices. Another concern here is your introduction of harmonics. As you know, here in the converter we are using the power electronics devices, and these devices are using some off and on control, so means we have to use the firing circuit. Due to this off and on, they never produce the perfect sinusoidal, and therefore some harmonics are introduced in the system and they are not good. No doubt we use some filters to filter out these harmonics. At the same time, some of the harmonics, they enter into the system. Especially we use the filters for the lower order harmonics, but higher order harmonics we allow to enter into the system. The reason behind that, for the lower order harmonics, they are having the large in the magnitude. In the magnitude of the lower order harmonics are higher, and also the filters require the size will be less. So normally we filter out this larger magnitude of harmonics, and the smaller magnitude of harmonics we allow, because it is not possible to go for filters for all the harmonics. And at the same time, there are the two types of harmonics. One is your characteristic harmonic, another is a non-characteristic harmonic. If you are using a 6-pulse converter, so normally this harmonics H is nothing but your NP plus minus 1 harmonics. Here N is your nothing but your starting from 1 to it is integer value, and P is your pulse number. So for 6-pulse converter, here we are going to have 5th, 7th, and 11th and 13th harmonics. So the magnitude of this harmonic contents, basically they are called the characteristics harmonic. Other than that, also due to the overlapping of the current, because current cannot be changed instantaneously in the valves, so there is some changeover of current, so they introduce some non-characteristic harmonics, and it is not possible to the filter out. So but the larger order harmonics, we are using the filters, and they are not allowed to enter in the system. But at the same time, some of the harmonics they enter into the system, and we don't have any control over that. The major problem with the harmonics, if they are entering into the system, they will create more loss in the system. Means core loss will be more. There will be I square R loss may be also more, and at the same time there may be some possibility of the resonance with the rest of the AC power system, and that is very, very dangerous. Another problem with the HVDC system is the blocking of reactive power. Means here as we know, this if AC system is connected here, suppose we have this is one area and we have another area, this is connected by your DC system, so the reactive power generated in this area cannot be transmitted to this area 2, because this DC there is no reactive power transfer. So this blocks the reactive power of any of the area, means it will be here from area 1, it will not flow to area 2, or from area 2 it will not come to the area 1. Now question, why we want the reactive power? Sometimes in the emergency cases, let's suppose there is some generator outage, some of the emergency in this there is some fault, at that time we may require some reactive power support from the area 1 or 12, but it will block here. So it is not possible to transmit the reactive power to the area 2 or from 2 to 1 during the emergency condition. So it blocks the reactive power. But in the normal practice, we don't allow that reactive power should flow from one remote place to another remote place, because the reactive power concept is the localized concept, and it is related with the voltage of the system. Another major problem in the HVDC system is it is not possible to go for the tapping of the power at the different location. Means it is only that we can go for the point-to-point transmission. Means here from one node, here we are going another node, then the power which is flowing from here, it will be going here. It is not possible to tap the power in between. So it is not possible. In AC system, you know, once wire is going anywhere, you can tap the power. This is the problem of HVDC system. Why it is so? Because here the control which is here this station, converter station, and here converter station, they operate in the synchronous. Means here the information and here it will be the same. Means we require a very strong communication link between these two converter stations. So if the power is here going, you are taking, then we have to coordinate this another here some converting station. So what happens till now, although there are some researches going on, that we can go for the multi-point transmission, multi-terminal HVDC transmission system. If we are having only here from one end here the DC to here another, it is called two-terminal DC system. If you are taking here another DC system, here you are taking here 3-phase, here 3-phase, and here we are having 3-phase. So this is called multi-terminal HVDC. So far we have established only the 3-terminal HVDC system. So this is one of the major problem of the DC system as well. So here the point-to-point transmission is not possible. Is only possible in the DC system. However, in the AC you can tap the power anywhere in the system. Now let us see your complex this system. Now we have seen that the generation must be your AC system, because it is economical, convenient and the cheap to generate. At the same time, the utilization part, or you can say distribution or load type, we should go for the AC system. Now the question again only the remain open for the transmission system. Means we can go for your AC as well as the DC system. We saw the several advantages of your DC system compared to AC system. So then we can go for the AC and DC systems. Just we saw witness that the early power system development was very much localized. Means generator as well as the loads were very close together. But we realized that there was a continuous development of the voltages as well as the frequency. Then we had the standards for the voltage as well as the frequency, and we went for the integration of the system. So that we keep on integrating, we keep on adding the power system. So the present day power system is a complex, interconnected, and also it is varying in the size and configuration. Now again the question arises, why we started the interconnecting whole these generators as well as your load centers along with the transmission line. If you will see this interconnected power system have several advantages. Advantages include that in interconnected system that the total reserve capacity can be reduced. So the advantage here, first advantage of your interconnected power system. First, it reduces the reserve capacity, means reduces reserve capacity. Now, if you will see in the, for example, let us take a generating station here. This is of 50 megawatt. To understand the reserve capacity, just I am explaining here, and we have a load somewhere here. We have another, let's suppose load is your wiring, that is your 30 megawatt, and we have another station here that is, it is supplying here 50 megawatt, and here your load generator should be more than 50 megawatt. Now what happens? Now why we go for more? Because the load is increasing, we are going for the more reserve margins here. Now here also we have the 50 megawatt and our generating capacity should be more than 50 megawatt. Sorry. So if you can connect these two systems, now what will happen? Even though here this your load is 70, there is no need of this generator. Means here same generator can supply here and still we have the 30 megawatt reserve. So the due to the interconnection, we can reduce the reserve margin of the system, or therefore means we can reduce the installed capacity of the power system by the interconnecting. This is the one of the major advantage. Another advantage is that the capital cost. The capital cost per kilowatt is less for the larger unit. So with the help of interconnections, we can go for the larger units, and therefore we can reduce the total installation cost of the power system, and therefore it is possible to have the cheaper electricity generation. So the total capital cost, if you are going for the interconnected system, so we can increase the capacity of generators, we can go for the larger and larger size. That's why right now you can say we have, even our India, we have the generating a single unit can generate more than 500 megawatt, and this is due to the interconnection, because none of any city is having, even though in UP or somewhere you can see more than 500 megawatt. So with the interconnections we can reduce the capital cost of the power system. Third advantage that here that it is possible, because you know this loads here, this is keep on changing, and therefore if the load is very minimum, let's suppose here load has reduced to your 20 megawatt here, and this 20 means only we can run only one unit of generation. So it is possible that we can run the most effective unit at the higher load factor, and the inefficient station can be used at the peak hours only. So what will happen? Again, the total cost of the electricity generation will be reduced. Another advantage of interconnection that interconnection reduces the requirement of high installed capacity. The load curves of the two different stations are seldom identical, and the maximum demand is the less than the sum of the maximum demand of the individual stations. For the two different areas, the maximum demand, you can see, they will seldom occur at the same time. For our Indian system, if you will see that we have our peak demand, that is a 30 minutes difference from the northeast state to the central state. So the peak which occurs here at the 8 p.m., it will occur somewhere, it is 7:30 p.m. in the northeast. So what happens, then we can interconnect the power system, and that will reduce the total installed capacity of the power system. Also, by doing the interconnected power system, we can improve the reliability, and that is here this fourth is it reduces this installed capacity, and fifth advantage here is that is improves the reliability of the system. And your third was the effective use of generators, you can say. So it can improve the reliability of the system. Now we can see how it can improve the reliability of the system. For example, let's suppose earlier it was not having interconnected. If there was something problem in this generator, if this generator is tripped, this 20 megawatt load, it is not possible that we can feed this supply. So the reliability of this system, even though the tripping or there is some problem in this generating station here, it will be not, once it is tripped, it is not possible to supply this 20 megawatt. So the reliability of this system, it depends upon this reliability of this generating station. But if we can interconnect here by this one, even though this generator is tripped and there is some problem, it is possible to feed this power through this transmission line and to this here. But there is a possibility that this generator may not be capable of supplying complete power, but we can maintain some of the emergency services of the system here. Means we can feed some of the power, or we can reduce the power in this area, and finally we can supply it. So this reliability of the system is improved with the interconnection of the system. Now there are several problems in the interconnection. No doubt, if we have in any system, if we have some advantages, there will be some problems or disadvantages as well. The first disadvantage or drawback of the interconnection is that fault in one system will get propagated into the another system. For example, here if there is some fault here and there is a fault here at this bus, what will happen? This will be propagated here, and this generator as well as this generator, both generator will be tripped. So the fault in one system, it getting here in other system, it will be propagated, and that's why here it is sometimes very, very dangerous. We should have a very fast and reliable protecting device so that we can trip here. We can trip here this line, and we cannot allow this fault to propagate and transmit in this zone. But if we assume that if there is no interconnection here and the fault is occurring here, okay, this system will be intact and we can maintain the power supply in this system here, and this both are operating in isolation. So here the fault, as I said, if it is interconnected, here this will be, then fault will be coming here, and to have the more reliable power system, there should not be complete collapse, we should have the protective devices here, and so that it can isolate the faults, and then we can maintain the remaining part of the system in the healthy. So we saw the first major problem of the interconnection is that fault gets transferred to the other healthy areas, and for that we should require the very fast and the reliable switchgear, that is including your circuit breaker and the protecting devices, so that it should not get propagated. Another problem in this AC interconnection system is that the high switchgear rating is to be employed at the different point of the system. It means if you are keep on interconnecting the power system. For example, here if you are having, this is your bus, and here we are having the different lines, then the rating of here the circuit breaker, this circuit breaker, we require the higher rating. Means if you are keep on interconnecting more, suppose you are adding another line, then the rating of this circuit breaker may change. This is due to the fault level that will increase here at this bus will be increasing. So if you are keep on interconnecting, then the circuit breaker requirement will be keep on increasing. The example which we took, we saw here one generator and it was supplying here the load, and similarly another generator was here and it was supplying load at this here. If you are connecting this one as like this, so the rating of this circuit breaker earlier which was using, now we have to increase because the fault level at this point is increased. So we are going for the more circuit breakers here, more the transmission lines and circuit breakers, more switchgear equipment. At the same time, the rating of the switchgear equipments also increases. The third problem now is the proper management required to dispatch these generating stations. So here what we require, that there should be some energy management system and it is automated, so that we can operate these generator 1 here and generator 2 in the economical fashion. So we require the interconnected and the sophisticated tool, that's power management, in this power system. As you know, it is only 2 generators, but in an actual power system there may be 10 to 100 generators, and it is so many transmission lines as well as the transformers. So it is very much required that we should operate the power system in a such efficient and also to dispatch these generating stations in the economical manner. So normally for that we go for the economic load dispatch as well. Now you can see here in the power system that is more and more interconnected. We are having even the more than 100 generating stations and generators. So we require some generators should run as the base load, means they should continuously run. Some generators may require to run only at the peak load, and again this category basically depends upon that what is the cost of that generator or the available fuel. For example, a runoff river generator, means this is a hydro type. In hydro, here we have the different, like let's suppose hydro generators. We have your runoff river type of generator. We have the pondage type, that is a pondage or storage, and another is called the pump storage type of hydropower station. ROR is nothing that is called run-off river hydropower plants, means it normally if rivers are flowing, they are at the different small dams are there and we utilize these power. Suppose if you are not utilizing that power, what will happen? This will go in the waste. So the run-off rivers, they always use at the base load plant. Means whenever this river is flowing, you have to utilize, otherwise this energy will be going in the waste. So this ROR will be used at the base load power plants. Like the pondage, we can store the water and then we can utilize whenever it is required. So this pondage can be, depends upon your storage capacity, you can use at the base load as well as the peak load. But the pump storage power plant, this is the plant, this is a hydropower plant, they only use for the peak load. Means when there is a demand, we use it, and when there is a less demand, we can feed it water back to the storage. So this is called pump storage. So it is always used as the peak load power plant. The conventional power plants, if you see, now again we have to come what are the conventional power plant and what are the non-conventional power plant. The conventional power plants include your thermal power stations, the big thermal power stations. We also go for the gas-based power plants, and here it is a diesel power plants. They are known as the conventional power plant. Other than these power plants, here they are called the non-conventional. Here hydro also comes, big hydro power plants, they come under the conventional power plant. In the non-conventional power plants, and they are also called the green power, like your solar, wind, fuel cells, they are coming into the non-conventional, and they also called it the green power because they create less pollution to the environment. So here the thermal, basically they use the coal, and then we burn the coal and then we generate the steam, and steam becomes the media of the transfer of power from heat to again go for the mechanical, that turbine we run, and then turbine runs the generator, and then finally we generate the electricity. So this power plant can again run both as peak as well as your base load plant. However, the diesel, as you know, the diesel cost is more than coal, so it always run as the peak load power plant. Your gas is also, it is very quick in starting. Here in the thermal power station, it is not quick in starting. Normally a thermal power station, if it is in the hot roll state, means it is running state, then it can require even the 4 to 5 hours. If it is in the cold state, means all the boilers there is no heat in the boiler, etc. So it is called cold roll state, and then it may require 7 to 8 hours. So here the thermal stations requires more, so it is not possible quickly you can turn it on, it requires some time. But the gas and diesel, they are very quick and we can start, so they can be used for the peak load power plants. Another is here the nuclear, that is very important, and nowadays our government is very keen to go for the more nuclear power plants, as now we have the limited gas, limited diesel, limited coal, so the option that we can go for the nuclear, because hydro is also very limited in the sense that we are facing a lot of hesitations for the dams and other things, because there are the environmentalist people, they are always opposed that we should not build the large dams, so that there are so many areas are submerged, and they are creating a lot of problems. So the another option is the nuclear, and we have the huge reserve of thorium as well as the uranium. So the nuclear power plants, they can also run as the base power plant, and they normally run as the base power plant, because here the nuclear, due to the safety in other regions, it is not possible to quickly stop and quickly turn it on. So here, and the cost of generation of the nuclear power station, the cost of generation is very, very cheap, but the total cost is very high, because we go for the very safety factors, and again people are very much afraid about the nuclear power plant. But now we have the future for the nuclear power plants as well. So always here the operation of the power plants depends upon the following criteria, that the cheaper electricity generating units should be used as a base power plant. The highest starting time generating plant is also used as the base power plant, and the size on the plants is also a decisive factor. Means what is the size? If the size is very small, then quickly you can start and stop, but if the large size, then we may require large time as well. So this in interconnected power system, the generators, as I said, they are normally loaded, they are running based on these criteria, that which will be running at the base and which will be running as the peak load. Some of them may run for the both purpose, again depending upon the requirement of the system. Now we witness that now power system is highly complex, interconnected, and due to the increased loading of the power system, it is always our intention to operate power system in most of the reliable, secure and stable condition, so that we can supply the power to the customers in the reliable, and also our intention is to supply the cheap, means economical electricity to the customers. In India, the power system in the most of the states are owned and operated by electricity boards. Now again, these electricity boards are broken into the different boards. So earlier this generation, transmission and the distribution was in the state was responsible. It was responsible means by basically your state electricity boards. They were operating your generating stations, transmission lines as well as the distribution system. And again we have presently the 5 regional electricity boards. One is your Northern Regional Electricity Boards. Another is Western Regional Electricity Board. And your southern, like we have your NREB, that is called Northern Regional Electricity Board. We have the Western Regional Electricity Boards. We have the Southern Regional Electricity Board. We have Eastern Regional Electricity Board. We have Northeastern Regional Electricity Board. So in India we have the 5 regional electricity boards. Means in Northern Electricity Regional Boards we have the several states. They are interconnected, and this includes your Haryana, Himachal Pradesh, Delhi, Punjab, Rajasthan, Jammu and Kashmir, Chandigarh, Uttar Pradesh and Uttaranchal. Similarly, we have the Western Regional Electricity Board. The several states are interconnected. In the Western Regional Electricity Board, it is Gujarat, Madhya Pradesh, Maharashtra, Goa, Daman Diu, Dadar Nagar Haveli and your Chhattisgarh states. They are coming in the Western Regional Electricity Board. The Southern Regional Electricity Board comprise Karnataka, Andhra Pradesh, Kerala, Tamil Nadu, Pondicherry and the Lakshadweep. In the Eastern Regional Electricity Board, it is Bihar, Andaman Nicobar, West Bengal, Sikkim, Orissa and the Jharkhand they are coming. Most of the states they are interconnected and then we are operating the power system in the regional basis. And these regions are also now getting into the, they are getting connections interconnected. So most of the region already they are northern and the Western Regional Electricity Board they are interconnected. Now the goal of India that we should have a national grid means all this here regional electricity board must be interconnected and then we can supply and with this grid we can operate our system efficiently. Again the different state even though this northern regional electricity board and the western regional electricity board they comprise together more than 60% of your installed capacity means they are having the lion's shares and the remaining here 40% comes under the southern region, eastern region and the northern eastern. Northern eastern region basically comprise of Assam, Arunachal Pradesh, Meghalaya, Nagaland, Tripura and the Mizoram. So here we have a good potential of hydro in these regions and they are having the surplus amount of power. However, other regions, mostly here the western and northern, they are in the deficit of power. So now we are just trying to have the interconnection from the northern region and northern eastern region to other regions so that we can transmit power from the northeastern region to the deficit area that is western and the northern region. Again now we can see here the interconnection. Now we can summarize how our power system is interconnected. We can see here we have the different generating stations like here generating station. We have the several generating stations and we have seen that generating stations cannot generate power at the higher voltage. Till now in India we have the highest voltage generation of 21 kilovolt. However, in the world it is 33 kV. But we know that if you are going for higher voltage, the losses in the system is less and at the same time we can transmit bulk amount of power. So our intention to keep on increasing, already I give information about the evolution of power system where we saw that the increasing in the voltage level in the transmission system, it is witnessed that we have to go for the higher voltage transmission system to reduce the loss and to transmit bulk amount of power. So these generating stations, they generate power and then we use the generating transformer. It is normally called the GTs it is very near to this generating stations. So they step up the voltage of these generating like here I have written here 21 kV. Here some of the generating stations they are generating at the 11 kV. Normally the 500 class of megawatt generators they are generating at the 21 kV. Here the 21 kV means it may be 20, it may be 21 point something, means the per unit voltage is 21. Those are here 200 megawatt or 220 megawatt generating stations. They normally generate at the 16 kV. And the remaining that is 100 or 110 megawatt generating stations, the generating voltage are normally 11 kV also. So we use the generating transformer to lift the voltage either at the 400 or at 220 kV or even at 132 kV depending upon the evacuation of power from these generating stations. Our ultimate aim that these generating powers must come to our small customers and then it will follow the transmission lines. It also sub-transmission system and then it is here the primary distribution, this is the distribution system. So the integrated transmission system, it is having presently we have the 800 kV transmission system, 220 kV transmission system and 132 kV transmission system. Presently we have the transmission line that is constructed at the 765 kV class of insulation. Normally it is called 800 kV transmission system, but presently it is operating at the 400 kV transmission system. We have the Anpara and Unnao line. It is very near to us. The line is built on 800 kV class of installation, but presently it is operating at the 400 kV 400 kV board, because later it is assumed required of the more power evacuation. We can go for the higher voltage. Once line is constructed, only we have to change the terminal equipment of this rating. Then we have in this system we have the several interconnecting transformers. They may be of 400 by 220, 220 by 132, and so on and so forth. So these are the transformers that are existing, and normally they are called ICTs, power transformers. Then from lower voltage we go for this other transformers, and then we try to reduce the voltage at the lower voltage. It may be directly 66 kV, it may be 33 kV, the distribution side, and we also feed power to the large customers at the higher voltage as well. Even though some of our customers, they take, like your railway, takes power at 132 kV. Even though some big companies like the Fertilizer Corporation of India, FCI, they also take power at 132 kV. So we have the intertie lines, and also we supply to the very, very large and the large customers. Those require power at very high voltage as well as the high power. Also we go for the medium type of voltages, and the medium customers, they take the power at 33 kV or 25 kV, like your railway. The traction purpose, they normally use 25 kV and the 11 kV transformer. At the same time, you can see there are some small generating units. These small generating units, they are nothing but they are maybe the captive power plants, or nowadays there is another concept that is called the distributed generators. They are coming into the distribution side so that we can reduce the transmission, you can say T&D losses, etc. And finally here, after that transformation, we have the two type of distribution system again can be classified in terms of the primary distribution and the secondary distribution. Secondary distribution is your 400 volt, and it is of 3 phase, and single phase it is under 400 divided by under 3, that is we get the 220 volt supply, and it is finally given to the small customers. So the medium customers can take the any voltage more than even the 400, but the small customers, they take here. So this is overall practice of, you can say, the structure of the power system. We have the generating stations, then we lift the voltage with the help of generating stations, and then we have the different interconnecting transformers, and then finally it is reaching to the small customers as well as the other customers. So nowadays there's a lot of people are interested in the small generating units, and we are putting in the distribution system to improve the system performance, and this is called the distributed generators. We'll see again the various advantages of the distributed generators in later lectures. So with this now I can conclude, I can recap. We saw the evolution of power system, how we just earlier we had isolated power system with the different voltages. It was AC and DC, finally it came to the AC, and then we interconnected all the system, and now our generators are mostly the AC. The utilization is AC, but this system, that is a transmission part, includes your AC as well as DC power system. So this is a highly complex power system, that is the generation is AC, utilization is AC, however the transmission part is AC as well as DC. And since our demand is keep on increasing, we are keep on adding the generating station, this system becomes very complex and very nonlinear in nature. Thank you.